What if the very star that gives us life is also silently plotting our end? Every sunrise tells a story, one that began 4.6 billion years ago and ends in cosmic fire. But this isn't just the story of the sun. It's the story of us, born from stardust and destined to watch our star fade. Welcome to the greatest fire in our solar system, the sun. It's the heart of our planetary neighborhood, the reason we exist, and one day, the reason we might not. Today, we dive deep into the life story of our star, from its mysterious birth to its inevitable death, and how this fiery sphere has shaped everything we know. In the vast expanse of the cosmos, our sun is but a speck. Yet for Earth it is everything, our clock, our engine, our shield. Its light bathes us every day, stirs the winds, and feeds the forests. Its warmth melts glaciers and sparks the churn of clouds. And while we bask in its glow, we rarely pause to wonder about its own journey. How did this celestial giant come to be? What forces forged it, and what legacy will it leave behind? To unravel the life of the sun is to confront the forces that shape existence itself. Picture a time before planets, before Earth itself. A swirling, silent darkness interrupted only by the occasional flash of distant stars. It's here, in this emptiness, that our story begins. About 4.6 billion years ago, in a quiet arm of the Milky Way galaxy, a massive cloud of gas and dust drifted through space. This was a cold and lonely place, filled with hydrogen and helium atoms, the leftovers of even older stars, long gone and scattered. These cosmic clouds, called nebulae, are the wombs of stars. For millions of years, this cloud floated undisturbed, but a disturbance, perhaps the shockwave of a nearby supernova, ripples through, triggering a slow collapse. Gravity, the ever-patient sculptor of the universe, begins its work. Particles of dust and gas draw closer, clumping together, growing denser and hotter at the heart of the cloud. As the material condenses, it forms a spinning disk, with most of the mass gathering at the center. Deep within this dense core, the pressure becomes unimaginable. Temperatures soar to millions of degrees. At these extremes, atoms are stripped of their electrons, and the rules of ordinary chemistry break down. Then, in a moment both violent and serene, nuclear fusion ignites. Hydrogen atoms smash together to form helium, releasing energy in the process. In that instant, a star is born. Our sun, a G-type main sequence star, emerges from the darkness. Its light begins to shine, pushing back the shadows and announcing its arrival to the newborn solar system. But the birth of the sun isn't just a singular event. Around it, the leftover material begins to coalesce. Tiny grains of dust stick together, forming pebbles. Pebbles gather into boulders, boulders into planetesimals, and planetesimals into planets. The solar system takes shape: Mercury, Venus, Earth, Mars, and the distant giants, each world a product of the sun's gravitational embrace. The sun's early years are tumultuous. Fierce winds of charged particles blow outward, sweeping away the last traces of the nebula. These solar winds help determine which planets will keep their atmospheres and which will be stripped bare. The sun's gravity anchors the planets in their orbits, setting the rhythm of days, years, and the slow dance of the ages. At the heart of the sun, a never-ending battle rages. Gravity tries to crush the star inward, while the energy from nuclear fusion pushes outward. This delicate balance, called hydrostatic equilibrium, keeps the sun stable. For billions of years it will maintain this harmony, shining steadily, nurturing the planets that depend on its light. Our sun is just one star among hundreds of billions in the Milky Way. Yet it is the center of our story, a beacon in the cosmic dark, shaping the destiny of everything in its orbit. But what exactly is the sun? To the naked eye, it appears as a brilliant, blinding disk in the sky. Yet, beneath its dazzling surface, lies a structure as complex as any living thing. The sun isn't a uniform ball of fire. It's layered, dynamic, and full of mysteries. At its very core, where temperatures exceed 15 million degrees Celsius, nuclear fusion blazes. Here, hydrogen atoms are forced together, forming helium and releasing an astonishing amount of energy. Every second, the sun fuses about 600 million tons of hydrogen, converting a small fraction of that mass directly into energy. This process powers the sun and, by extension, all life on Earth. Surrounding the core is the radiative zone. In this region, energy generated by fusion travels outward, but not in a straight line. Photons, the tiny packets of light, are absorbed and re-emitted countless times, bouncing from atom to atom. It can take a single photon hundreds of thousands of years to make its way through this dense zone. Above the radiative zone lies the convective zone, where the sun's energy sets vast currents of hot plasma in motion. Hot material rises toward the surface, cools, and sinks back down, creating swirling patterns like those in boiling water. These currents generate powerful magnetic fields, which can twist, snap, and reconnect, occasionally unleashing solar flares and eruptions. The photosphere is the surface we see, a thin layer, just a few hundred kilometers thick, where the sun's light finally escapes into space. Here, dark sunspots appear, marking regions of intense magnetic activity. These sunspots can last for days or weeks, changing the sun's output, and even affecting Earth's climate. Above the photosphere is the chromosphere, a region of reddish glow visible only during solar eclipses. Jets of gas, called spicules, shoot upward, carrying energy into the next layer, the corona. The corona, the sun's outer atmosphere, is a puzzle. It is millions of degrees hotter than the surface below, a paradox that still baffles scientists. The corona stretches millions of kilometers into space, its wispy tendrils visible as a ghostly halo during total eclipses. From the corona, the solar wind streams outward, a constant flow of charged particles that fills the solar system. For centuries, these layers remained hidden from view, their secrets locked behind the blinding glare of the sun. But in recent years, new technologies have pulled back the veil. Spacecraft like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter have journeyed closer to the sun than any probe before, braving intense heat and radiation to send back detailed images and data. These missions have revealed the sun's turbulent surface, the tangled dances of its magnetic fields, and the origins of the solar wind. They have shown us that the sun is not a static object, but a living, breathing entity, full of storms and surprises. The sun's influence extends far beyond its visible light. Here on Earth, it is the master of our climate, the driver of our weather, the engine of life. Every beam of sunlight carries energy that fuels the planet's ecosystems. Plants use sunlight to perform photosynthesis, transforming carbon dioxide and water into oxygen and sugars, the foundation of the food chain. Without the sun, there would be no forests, no oceans teeming with life, no animals roaming the land. The sun also drives the water cycle. Its heat evaporates water from the oceans, lakes, and rivers, lifting it into the atmosphere as vapor. Winds carry these clouds across continents, where they release their cargo as rain or snow. This endless cycle shapes landscapes, carves valleys, and nourishes crops. Yet the sun's power is not always gentle. Solar flares, sudden bursts of energy from the sun's surface, can send waves of radiation hurtling toward Earth. Even more dramatic are coronal mass ejections, or CMEs, which launch billions of tons of plasma into space. When these storms strike Earth, they can disrupt satellite communications, knock out power grids, and create dazzling auroras near the poles. Our planet's magnetic field acts as a shield, deflecting most of the solar wind and protecting us from the worst effects. But it's not perfect. In 1859, a massive solar storm known as the Carrington event caused telegraph systems to spark and catch fire. If a similar event happened today, it could cripple our technology-dependent world. That's why scientists watch the sun closely, using a fleet of spacecraft to monitor its moods and predict its tantrums. The Parker Solar Probe, launched in 2018, is flying closer to the sun than any previous mission, sampling the solar wind and measuring the sun's magnetic fields. The Solar Orbiter, launched by the European Space Agency, is providing high-resolution images of the sun's poles and surface. Together, these missions are helping us understand, and one day, perhaps predict, the sun's behavior, giving us time to prepare for the next solar storm. But even as we study the sun's present, we cannot ignore its future. The sun is not eternal. It is a cosmic clock, ticking steadily toward its final act. Right now, the sun is in its stable, middle-aged phase, known as the main sequence. It has been here for about 4.6 billion years, and has enough hydrogen to last for roughly 5 billion more. But this stability is temporary. Over time, the sun's core will run out of hydrogen fuel. As fusion slows, gravity will begin to win, compressing the core and raising temperatures even higher. The sun will respond by expanding outward, growing brighter and hotter. In about 1 billion years, this gradual brightening will have dramatic consequences for Earth. The increased heat will cause the oceans to evaporate, stripping away the atmosphere and making the planet uninhabitable. Life, if it still exists, will be forced underground or into the far reaches of the solar system. As the hydrogen in the core is exhausted, the sun's outer layers will balloon outward. It will become a red giant, swelling to hundreds of times its current size. Mercury and Venus will almost certainly be engulfed. Earth's fate is less clear. Some models suggest it will be swallowed, others that it will be scorched and pushed outward. Either way, our planet's days as a cradle of life will come to an end. During this red giant phase, the sun's core will contract further, reaching temperatures high enough to fuse helium into heavier elements like carbon and oxygen. But the sun is not massive enough to ignite the fusion of even heavier elements. After a few 100 million years as a red giant, the outer layers will be blown away, forming a glowing shell of gas called a planetary nebula. At the center, all that remains is a dense, hot core, a white dwarf. This stellar ember, about the size of Earth but with half the mass of the sun, will glow faintly for billions of years before fading into darkness. The sun's journey, from birth to death, will be complete. What does this cosmic tale mean for us? The answer is both humbling and inspiring. We are quite literally made of stardust. The carbon in our cells, the oxygen we breathe, the iron in our blood, all were forged in the cores of ancient stars, scattered across the galaxy by supernovae and gathered into new worlds. Our sun is part of this grand cycle, a link in a chain that stretches back to the dawn of time and forward to the far future. The sun's story reminds us that life is a fleeting miracle, a brief spark in an ever-changing universe. Our existence depends on a delicate balance of forces, maintained by a star that is neither too hot nor too cold, too young nor too old. Yet, as we face the challenges of a changing climate, resource scarcity, and our own technological risks, the sun offers both a warning and a promise. The same energy that sustains life can also threaten it. Solar power, harnessed wisely, could provide nearly limitless clean energy, reducing our dependence on fossil fuels. Advances in solar technology are making this dream a reality, with new panels, batteries, and grid systems transforming the way we power our world. At the same time, scientists are exploring ways to protect our planet from the sun's more dangerous outbursts. Concepts like space weather forecasting, solar shields, and even geoengineering are being studied as possible defenses against future threats. But the sun's influence isn't limited to technology and survival. It shapes our cultures, our myths, and our sense of wonder. From ancient sun gods to modern solar observatories, humanity has always looked to the sky in search of meaning. The sun reminds us that we are both powerful and fragile, capable of great achievements yet dependent on forces beyond our control. As Earth's climate warms, some scientists are studying the planet's natural ability to regulate carbon dioxide. Processes like silicate weathering, where rain reacts with rocks to lock away carbon, act as a slow but steady thermostat. Others are considering more direct interventions. Solar geoengineering, for instance, proposes reflecting a small fraction of sunlight back into space to cool the planet. These ideas are controversial, but they reflect a growing awareness that our fate is tied to the sun's energy. Can we use science, technology, and wisdom to protect our species, not just for centuries, but for eons? The answer is not yet clear, but the sun's story urges us to try. Let this be a reminder. Every sunset is a message from the cosmos. Our sun is a ticking clock, both a gift and a warning. The more we understand it, the more we understand ourselves. Let's appreciate this glowing titan, not with fear, but with wonder, innovation, and gratitude. For as long as it lasts, the sun will continue to shine, lighting the path for Earth and its inhabitants. And when its time comes to an end, it will leave behind not just a white dwarf, but a legacy of life, energy, and the unbroken chain of creation. If you found this story of cosmic beauty and existential truth meaningful, take a moment to reflect on your place in the universe. We are children of the sun, bound to its fate and its fortunes. Share this story with someone who needs a little perspective today. And remember, the universe is watching. The sun's journey is our journey. Let's make it count.